Okay, here we go. Unit 5, Lesson 8. So I'm pretty psyched about this. I bought, at Advisory Bonding Day, I bought some giant playing cards. But I had an idea because I know the Unit 5 art project is coming up, which went so well last year that I want to do it again. But I started creating mine. I want to kind of lead by example as your teacher, and it's also fun for me. But basically, you have like one page to capture like most of the concepts from Unit 5. You can use it as a cheat sheet. It builds this really critical skill in geometry of being able to draw like representations of concepts, which is super fun to me. But anyway, I realized I forgot one of our lessons with the Play-Doh. I used Play-Doh with a plane to cut through Play-Doh. Awesome prop to use in class. I think it really helps to visualize things, but I had forgotten the giant playing cards. So what we're gonna do as a class for the Unit 5 art project is we're gonna create our own giant geometry playing cards. So we're just gonna create our own. That way we'll have, they'll be even cooler than these because they'll have all your work and all your art. So future classes can see like what you did this year. And your work will live forever, which is kind of cool, I think. So anyway, here we go. Oh, there's the Unit 5 art project from last year. I'm also trying to get approval for the San Francisco field trip. We're getting closer. Initial feedback has been good. We just got to get official approval. But the plan is the top 25 people across all my classes that participate the most will get to go to the Transamerica building in the morning. And then in the afternoon, we're going to go to Giant Stadium. So we'll go into their house and see what the stadium looks like. So anyway, we are cooking in geometry. I hope we'll be able to get this approved. The norms, you gotta always follow the norms. Music, hey, Strung Out, love that band. Solid Geometry, Cool Down, Incredible Hulk, we'll skip ahead. This is one of my favorite Strung Out songs. Okay, 8.1, page 259. So lesson 8, speaking of scaling, let's practice moving back and forth between scale factors for lengths, surface areas, and volumes. So the formulas you need are length times K equals L prime, area times K squared equals A prime, and lastly volume times K cubed equals volume prime. So that's what you need to know. The image shows a cone that has a base with area 36 pi square centimeters. So we're going to say area equals 36 pi cm squared. That's what that is. The cm squared, don't let that confuse you. This is the one that we really need for the math. The cone has been dilated using the top as a center. Top vertex is known as an apex. Apex, let's see, we'll put a sharp drawing as well. Alright, so you got the apex predator, right? Anyway, just trying to have some fun. So an apex predator is the top. Top of the cone is an apex. All right. The area of the dilated cone's base right here is 729 pi square centimeters. So what you're going to say is A prime, because it's the dilated base, is 729 pi. What was the scale factor of the dilation? Well, you go back up to your formula box. Like, all right, which one do I need? Well, you need the A with the A prime. You need this one right here. So, area times K squared will equal area prime. So you just go, and I want to set the finish up. This is called setting up your finish. So we got to figure out what the scale factor is. So K equals. So what we're going to do is rewrite this right here. So you say A times K squared is A prime. A is 36 pi times K squared. A prime is 729 pi. Next thing you got to do is you got to start to chip away at this K squared. You want to get this K squared by itself. Isolate K is the goal. So to do that, you just divide by 36 pi to both sides. These are out of here because it's the same. These two pi's are out of here. So you're going to get K squared equals 729 divided by 36. So I could do that with written division. I could try it in my head, or I could just go to the easiest tool ever. Use the calculator. So 729 divided by 36 equals 20.25. So K squared equals 20.25. Now, we need to get K by itself. We can't say the scale factor is 22.25 because that's the scale factor squared. K is the scale factor if it wasn't already obvious. So what you got to do is you got to take the square root of both sides. Square root of K squared is just K. The square root of 20.25. On this calculator, you just say, in most of our calculators, you say second x squared 20.25, because above that x squared is the radical sign that you need. Then you just hit enter, and you're going to get 4.5. So K equals 4.5. K equals 4.5. There you go. Scale factor of the dilation is 4.5. Working on my Spanish. Alright. That was 8.1 going backwards. Unit 5 so far. So one of the things that you need to do in class is write all these down. And then we're going to draw pictures of all of them. Cube root. Ways of being smart at math. Ooh, problem card 1, data card 1. I love this problem. Here we go. Need some more expo stuff. Alright. So, we are going to use... Now, this is not in your workbook. You had to come to class to get this document. But data card 1 and problem card 1 go together. Data card 2 goes with problem card 2. So the problem says, a rectangular prism was dilated. Your partner has some information about the dimensions, surface area, and volume of the original and dilated prisms. Draw the original prism, labeling its height, width, and length. So, okay, so prism, it's a rectangular prism. So So I need to draw a rectangular prism labeling height, width, and length, and it's the original one. So here we go. Prisms are pretty easy, especially rectangular ones. So we've got this three-dimensional solid. Okay, so we gotta get a height, a length, and a width. That's the goal. Now, I know one of them's bigger than the other, but let's figure out which one. So the original prism's volume is 30. So we're gonna say V equals 30. You don't want to miss this cubic centimeter. That'll help you at the end. All right. The dilated prism's volume is 240 cubic centimeters. So let's make it a little bit bigger, just a tiny bit bigger. Just for the drawing's sake. I don't want to mess this up. Alright, so this is about the same shape. Could you get it perfect? Yeah, you could. Let's use the ruler. Okay, so you have two rectangular prisms. The dilated prism's volume, so volume prime, is 240 centimeters cubed. Now I would just call a timeout right there. You've got volume and volume prime, meaning that you can say V is K cubed with V prime. This is a huge piece of information. So we can knock this out real quick. We could get the scale factor. So what you're going to say is 30 K cubed equals 240. Divide by 30. Divide by 30. K cubed equals 8. Then you take the cube root. So you got to get the cube root of 8 to figure this out. So on a calculator, here's my guidelines. So I gotta hit 3-second up arrow number. So 3-second up arrow 8. 3-second up arrow, and then you hit the number. So one more time. 3-second up arrow 8. 2. So K equals 2. Huge piece of info. And if you want to like box this up somehow so you remember, K equals 2. Alright, the length of the original prism is 5. So 1 down. It's given. Length of the original prism, 5. So let's just write that in. And here we go. It's 5. Okay? The height of the dilated prism is 4. Okay? That means, because the scale factor is 2, that then this has to be 2. Because 2 times 2 equals 4. Now, volume is 30 cubic centimeters. The volume formula for the prism is length, width, height. So we are almost there. That means that L, W, H 30. L is 5 times W, we don't know yet, times height, which is 2, is 30. 5 times 2 is 10, so you're going to get 10W equals 30. Now you divide by 10, divide by 10, and you're out of here. W equals 3. 3. Did we draw the original prism? Yes. Did we get the height? Yes. Did we get the width? Yes. Did we get the length? Yes. 2 by 5 by 3. Alright, let me erase and move on. I'm going to try to teach you like the simplest way to do these. You'll notice they give you a bunch of stuff that you didn't even really need down here because we already got the scale factor. But you could use these to triple check your work. So surface area, you could go 62 times k squared should equal 248. So the 62 times 4 equal 248. It sure does. Alright, problem card 2. A cylinder was dilated. Your partner has some information about the dimensions, surface area, and volume of the original and dilated cylinders. This one says you gotta find the volume of the dilated cylinder. So because I did the dilated one over here, I'm gonna do the dilated cylinder over here. Let's just see which one's bigger, because in dilations you can get smaller, remember that, so be careful. So the original cylinder surface area is 80 pi square meters. The one thing I missed up here is these are centimeters. Missed my labels, of course. Anyways, so original cylinder surface area is 80 pi. Excuse me. The dilated cylinder surface area is 1280 pi. That means that the dilated cylinder is bigger than the original, meaning that the scale factor has to be greater than 1. Has to be. But let's chip away at these. So let's draw your original cylinder here. Draw a bigger one here. Okay. So we got 2 cylinders. All right, original cylinder surface area. So you're gonna say SA equals 80 pi square meters. The dilated cylinder surface area, so surface area prime, that's what that means, is 1280 pi. That's where I would just call a timeout and try to figure out, like we did here, what the scale factor is. But you need to know the formula. So the formula is SA k squared equals SA prime. So the original surface area times the scale factor squared equals the new surface area. So let's just start putting these in. We got SA, so we have SA prime. So you're going to say 80 pi times k squared equals 1280 pi. Divide by 80 pi. Divide by 80 pi. These are all out. So you're going to get k squared. These 2 pi's are gone. The 2 zeros are gone. So 128 divided by 8. I think that's 16. Yep. So k squared equals 16. You could have used the calculator for that. 80 times 10 is 80. 8 times 6 is 48. So yeah, 128. Okay, cool. So if k squared is 16, then k equals 4. And you need to like circle star, underline it, whatever, highlight it, whatever works for you. But we now know that the scale factor is 4. Okay? We need the volume of the dilated cylinder. Let's just chip away at what else we're given. So the radius of the original cylinder is 5 meters. So it's a pretty big cylinder. 5-meter cylinder. The height of the dilated cylinder, the height is 12 meters. The volume, they made it easy. The volume of the original cylinder is 75. So 75 pi cubic meters. What is the volume of the dilated cylinder? So we got to figure out the volume of this one. And we're going to call it V prime, because it's the dilated one. So, what are we going to use? We're going to use this formula again. Because we have the original V, we have the scale factor 4, we just got to get the volume prime. So this one's pretty easy. You just rewrite your formula, which is V k cubed equals V prime. Let's start plugging things in. So V, 75 pi. K, 4 cubed equals V prime. We're almost there. 75 pi times 64 equals V prime. Because 4 times 4 is 16. 16 times 4 is 64. 75 times 64. Let's see if I can do it in my head. Just kidding. I know the answer. So, volume prime. We're going to go to a calculator for that. 75 times 64 is 4,800. Don't forget about the pi. And don't forget about your label, like I did earlier. So, volume equals 4,800 pi cubic meters. Yay, we're done. We got the volume of the dilated cylinder. Volume, dilated cylinder. Okay, that was 8.2 on page 260. Halftime is always fun. Let's go to 8.3, jumbo can. This is a tricky one. Very, very tricky. Okay, so a beverage company manufactures and fills juice cans. All right, juice cans. So maybe use a prop here. Jumbo juice. I really dig these. Got a little bit of caffeine, and there's only 5 calories, which is kind of cool. sparkling ice. Jumbo juice can. All right. So a beverage company. Let's see which beverage company we're talking about here. Talking Rain Beverage Company. Sweet. Got one. All right. They manufacture and fill juice cans. Happens all day, every day for this company. They spend 4 cents on materials for each can. Wow. So this can, 4 cents. And they fill each can worth 27 cents of the juice. So what's the old cliche? The juice is, whatever. I don't know. So the juice inside the can is worth 27 cents. The can itself costs 4 cents. All right. The marketing team, these are the people trying to make the big bucks. I used to be in sales. In the business world, it feels like it's all about the bottom line. But the marketing team wants to make a jumbo version of the can that's a dilated version of the original. That happens all the time. Like, think about like dog food or Coca-Cola. Like, they have the little mini cans and then they have the big one. Red Bull is a good one. It's the same exact shape, but it just gets bigger. So, all right, dilated version of the original. They can spend at most 16 cents on materials for the new can. Original one, remember, was 4 cents, so we're going to do a big old one. There's no restriction on how much they can spend on the juice to fill each can. Well, that's good. They got some flexibility. The team wants to make the new can as large as possible given their budget. Okie doke. Number 1, by what factor will the height of the can increase? Explain your reasoning. Yeesh. All right, so we need the scale factor. Now there's a couple tips. Materials, so the can is going to be surface area. The fill costs, so in other words, the juice value, we're going to call it the volume. So let's write down what we're given. We are given 4 cents on materials. Materials, surface area. So SA equals 0.04. All right. 27 cents worth of juice. That's going to be volume equals 0.27. So our original surface area, original volume. Okay, marketing team wants to make a jumbo version of the can that's dilated. They can spend at most 16 cents on materials. Materials are surface area. So 16 cents is surface area prime, 0.16. No restriction on how much they can spend on the juice to fill each can. All right, so if I get the scale factor by using these two things, I can calculate the factor that the height of the can will increase. Because height times just K will equal height prime. So the height of the can times just the scale factor will equal the new height. So if surface area is 4 cents and surface area prime 16 cents, I can easily get the scale factor. So the formula that you really need is right here. SA times K squared equals SA prime. The surface area times your scale factor squared equals your new surface area. So, SA 0.04 times K squared equals SA prime 0.16 Now you're at algebra, which is easy. You're going to divide both by 0.04. 0.04. These cancel out. You will get k squared equals 16 cents divided by 4 cents. How many sets of 4 cents does it take to get 16 cents? 4? Because remember, like a quarter times 4 is $1. 4 cents times 4 is 16 cents. So k squared equals 4. Then you got to square root both sides. And you're going to get that k. Square root of k squared is just k. Equals square root of 4, which is 2. Put a box around this because it's going to help you so much. Now you can answer the question, by what factor will the height of the can increase? This is where you go to this formula. The height of the can will increase by a factor of this k by a factor of 2 because height changes by the scale factor. By what factor will the radius of the can increase? Well, here's your can. There's your radius. Just like the height, radius is also just like one dimension. So the radius will also only increase by the factor of 2. Cool. I'm gonna skip 3 through 6 just cause I feel like it, and but if you want to work on those and show me later, I'd be really impressed. But now you know the answer. Geometry and pasta. I'll play the video here. It's a really cool video. Should go on real quick. There it is.
Pasta. Delicious. Ubiquitous. Groovy.
In the world of pasta, it's a kind of a mirror world. It's the other side of the looking glass. Everything is absolutely groovy. This one's called Capelletti, little flats.
Architect Georges Legendre finds pasta's curves a delicious departure from the right angles of the everyday world.
This is a great video.
Environment. Everything's squarish.
Probably a genius.
More or less, the tables, the chair.
Anyway, he's an architect. He's talking about geometry of pasta. How cool is that? GOAT challenge. So if you get all A's on all 7 unit exams, you get 1 more title than Michael Jordan. So then I call you the GOAT. So you got to get 7. 1, 2, 3, 4, 5, 6, 7. So if you get 7, you're 1 more than Jordan. So I call you the GOAT. And then if you're a GOAT, you get snacks next year for free in my fridge. Sodas, whatever I got in the fridge is all yours. So it pays to be a GOAT, because every time you're like feeling tired or you need a little snack, you can just drop by my room. You earned it. It's so hard to get all A's on all 7. So if you work your tail off, I think you should be rewarded, which is how it works in the real world. So, GOAT challenge. All right, lesson 8 summary. This is a little dated. I think the Warriors are the 10 seed. Anyway, we'll move on. Participation MVP is me. Cool down. Oh, check the video. This was on quiz 3. It's a fun problem. And that is it for lesson 8. So thanks again for watching, putting in the extra work, and I'll be back shortly.